All right. Thank you. Thank you very much, organizer, for organizing this quite amazing program. And for them, it's been now the hand of third week in a row. So I really appreciate their commitment to Carrollian Physics. It's I know how hard it can be to be already twice in a row in a conference after another. So thank you for sticking around. I'm going to talk about a topic which is quite closely related to what Massimo talked about yesterday. In fact, I'm quite glad that he set the stage for me and introduced concepts which several concepts which I will reuse during the talk. But I also will explain some of the different approach that we're taking in this work done in collaboration with Laurent and Farouche, and the paper just came out a couple of weeks ago. It's been a long project, and I will explain along the way why it took us so long to actually finish this project. And but let me first give some motivation for what I'm going to present. So the idea is to start basically recall what people did early in the 20th century, that is to introduce the notion of elementary particle as irreducible unit representations of a group which is the isometry group of space-time. And in particular, using the concept of classical elements of the Lie algebra associated to this isometry group, then one can define irreducible representation of this Lie algebra. And these quantities, the Casimirs, correspond to physical quantities which represent conserved quantities. And the values of these quantities are what then labels the representations of this Lie algebra. Now, this works very neatly if in an absence of gravity, because there is a well-defined notion of isometry group of space-time. We can work with a fixed space-time. We can introduce the notion of isometry group, and then we can define elementary particle with respect to this isometry group. And the Casimir elements, as I was saying, these are conserved quantities that allow us to introduce, to study the system, in particular also the evolution of the system and the representation theory of the system. So things get a bit less clear when we introduce gravity, because in this case, particularly if we want to do quantum gravity at the end of the day, there is no fixed space-time. So there is really not a notion of a isometry group that we can rely on. And this approach of Bargmann-Wigner to define elementary particles as the reducible representation, unit reducible representation of the isometry group somehow becomes a bit complicated. The best thing we can do is to replace the isometry group with the notion of asymptotic symmetry group. That is, we fix an asymptotic structure of space-time, and then we define the asymptotic symmetry group as the set of elements that of bulk diffeomorphisms that preserves this asymptotic structure. So this leads to this notion of asymptotic symmetry group that acts on the gravitational phase space. And then the view of McCarthy already in the 70s was basically, he advocated for this approach towards defining these fundamental excitations of gravity as the irreducible unity representation of this asymptotic symmetry group. This was motivated his seminal work on the analogy, the study of a BMS group that I will review a bit in a second. In this case, then, so there will be conserved quantities, even in the presence of gravity, that one can define, and it will be relevant to study the representation theory of this group in order to somehow generalize the notion of spin and mass that one had, for instance, in the case of Poincaré, when we were talking about special relativity, for instance. And this is possible due to this notion of moment map that I will clarify along the way what it is. So this is somehow a bit the general framework. Now, the kind of Lie algebras that we will consider are of the form of the semi-direct sum. So they take this form here where there is a quotient K that act on an abelian normal ideal. So this symbol here is exactly telling us that this K acts by the Lie bracket action on these elements of this abelian ideal. In particular, we can introduce the notion of isotropy algebra, which is we take an element of the dual of this abelian ideal, and then we look for all the elements in K, that lives in K that preserves these elements of the dual algebra n star by acting with this coadjoint action on them. And so all these for each element of the ideal, there is then a notion of isotropy algebra associated to that. And this subalgebra has a very important role in the representation theory. In fact, it helps a lot to study the representation theory of the full group by just studying basically this subalgebra. This is what basically has been done by Wigner in the case of Poincaré, and that's also, as I was saying, what McCarthy was trying to do in the case of BMS, and we will see also the extension of BMS, and also the conformal Carrollian symmetries take this form here, so it would be relevant also in this case. Now, of course, the first example of an asymptotic symmetry group is the BMS group, which by now we all know very well. And this led to many attempts in the past to define a notion of angular momentum. There is a very extensive review by Zabados, but if you can see from the date, this was somehow predates all these developments that happened in the last few years, motivated exactly by this resurgence of interest in the BMS group. So the BMS group has this, semi-direct product structure where we have the proper orthogonal Lorentz subgroup, which acts on this abelian ideal, which is the group of supertranslations. So these are labeled by function on the sphere. Now, this index here, this number here, -1, relates to a conformal weight. It will become clear along the talk what I mean by conformal weight. It's a property of transformations of this function under conformal transformations. And then we know that there is, starting from this BMS algebra, there is a unique translation subalgebra that allow us to define the notion of Bondi-Sachs for momentum on scry. So far so good. However, as has been reviewed already by Massimo, there are some ambiguities when it comes to identifying a proper subalgebra of Lorentz inside this BMS. In fact, there is a list of ambiguities that comes with the BMS algebra. One of them is this, the most famous one maybe is what's called the supertranslation ambiguity, which was reviewed by Massimo. Basically, the idea here is that you can define a notion of canonical Lorentz subgroup by, if you have a given cut of scry, which is defined by this value of the retarded time u, given by a function of scry, this g of sigma. Sigmas are coordinates on the celestial sphere. And then you can consider conformal Killing vectors that live on the tangent space of the sphere. And the canonical Lorentz generators can be represented by these vector fields here, where there is this dependence on the cut that comes here, basically. And this is, we can see that this is a vector field which is tangent to the given cut that you have chosen by selecting this function on the sphere G. Now, the issue is that, of course, then it's a cut-dependent definition. And so if you have two different cuts, you have two different notions of canonical Lorentz subgroup, Lorentz generators, and you can go from one to another by doing supertranslation with a parameter delta G, which basically relates the initial cut to the final cut. So in this sense, there is not a canonical Lorentz subalgebra if you have radiation, because if you have radiation, the two cuts will be different in general before and after, and that's why this notion of canonical subgroup is ambiguous. Related to this ambiguity, there is another one, which is called the center of mass ambiguity. Here also the idea is that if you're in a stationary region, you can, first of all, the shear can be, you can kill the magnetic components of the shear and you remain only with the electric part. So you can write the shear in terms of this G here, this symbol here means symmetric traceless component of these two derivatives. This G, which is actually the same object here, it's what we call the electric supertranslation Goldstone. Will become clear, I think, later on why we call it Goldstone. And then you can go to a center mass frame by killing the shear, namely by setting this G to 0. This is what Massimo was also talking about yesterday. And again, the issue here is that in order you can go to this frame by killing G, but of course, if generically early time and late times, you have two different notions of Goldstone. So this defining the center of mass frame again is cut dependent as a notion. There is a third ambiguity, which is it's a rest frame ambiguity, in the sense that there is no canonical notion of a rest frame if we are in BMS, in the sense that in order to kill the total momentum, the Bondi total, the full total momentum, namely all the harmonics of the mass, with BMS is not possible. Again, this is something that is a condition, is a cut-dependent condition if you want to do that. So this, and we'll talk more about this ambiguity later as well. Yeah. But it is related to the first one. It's again this notion of cut dependence when you want to go to a frame where the shear is 0. It's really like, sometimes these two are presented as the same thing, but sure, but remember, if you want to kill like this goldstone, like for instance Massimo was trying to do yesterday, then there's again, you need to every time adapt your frame to the before and after. So in a sense, it's an ambiguity in that sense. Okay, it's you cannot give a unique definition regardless of the cut that you're choosing. Another ambiguity that maybe oftentimes is not presented is the fact that even if we know that, let's assume that we know what are the BMS charges associated to a conformal killing vector. So you give me a metric QAB, you have your sphere, and you give me the charge. This does not determine uniquely the charge aspect, the angular momentum aspect, if you're in BMS, because you can always shift your angular momentum aspect by a quantity which is symmetric traceless, this TAB, and with a derivative acting on it. And then, of course, when you integrate this on the sphere, with a vector field y, when you integrate by parts, this guy x on y, and since this object is symmetric traceless, this gives you 0. So the charge is the same, but the aspect now is it's shifted by this quantity. So there's kind of an equivalence class of aspects that you can define for a given charge, angular momentum charge. And finally, the one that in a way motivated our analysis was the fact that there is really no notion of spin generator in BMS, in the sense that, as I was mentioned before, the isotropy algebra plays an important role in Poincaré, and you can define the notion of spin by looking at the generator of this isotropy algebra. But when McCarthy studied the possible isotropy groups for BMS, so what you have to do, again, is to fix a given element of the ideal, and then look at the element of the quotient group that preserve these elements. You see that unless you are in the very specific case in which the mass aspect is a constant, in which case then there is a non-trivial Lie algebra, which SU2, or also in the case in which you have some axisymmetry in the mass aspect. But in the most general case, then the isotropy group is Z2. So there is no non-trivial notion of Casimir that you can associate with this isotropy algebra in the general case of a mass aspect that has no is not restricted to these two examples. So in a sense, there is no natural way to define a notion of spin as a Pauli Lubánski generator for BMS. And in fact, again, there is this subcase where one can say, okay, I can restrict to the case of a constant mass. There is an isotropy group which is SU2, and this in fact was used by Poincaré, Gralla-Y recently to define a notion of spin in a scattering problem. But as I will argue later on, this does not hold in the multi-particle scattering process, because in general, you cannot assume that the mass aspect, if you have scattering problem, lives in the coadjoint orbit of the constant mass aspect. So this notion of spin is only available if you only have a single black hole. So the outline is to, okay, first I will review briefly the case of Poincaré, because basically the leitmotif of my presentation would be a parallelism between what people did in Poincaré and trying to redo it in the presence of gravity. And this will be, so this just to basically list all the steps I will try to reproduce in the case of gravity. I will then introduce this generalized group, which is GBMS, and argue why this is the right frame to try to reproduce these steps that we can do in Poincaré. From this, we define the notion of spin generator as the generator of this isotropy algebra of this group GBMS. And then at the end, I will use this algebraic analysis to map things back to a gravitational phase space through the notion of the moment map. So this is a bit of the plan. So let's review the case of Poincaré. You are all familiar with this, so I will be quite fast here. The algebra of Poincaré, as I was mentioned before, this is a semi-direct sum. There is the Lorentz algebra here, the X on R4. R4 is the generators are the translation generators, this P mu, and the Lorentz generators, the angular momentum generators are this J mu nu. This is the bracket between the two groups. And then there are two Casimirs. In this case, there is a quadratic Casimir, which is the square of P. And there is a quartic one, which one can write as the square of this W mu. And this W mu is what we call the Pauli-Lubánski pseudo-vector that you can construct using the angular momentum generators and the four momentum generators. And this is the definition. The property of this object is that it is invariant under translations. You can check that it commutes with the translations, and it transforms covariantly under the Lorentz transformations. Moreover, you can also verify that it satisfies this algebra here. Now, if we diagonalize the momentum p, let's say we fix p to be a certain k mu, then this w mu preserves this quantity here. So in this sense, this object here is the generator of the isotropy subalgebra, which is SO3 subalgebra, which corresponds to the Lorentz transformation that preserves this vector k mu. Therefore, we can use the square of this object as one of the Casimir elements of Poincaré, and this provides an ambiguous definition of spin for a particle in a special relativistic setting. Now, important to understand better this notion of spin, it's useful to introduce the notion of a rest frame. So a rest frame is basically a frame in which the momentum only has zero spatial components, only has the time-like entry here, m. And this can be done by doing a boost transformation on a generic momentum p. So there's this lambda p that defines this boost that defines the rest frame. And then you can show that the intrinsic spin vector corresponds to the spatial components of this Pauli-Lubánski pseudo-vector if you go to this rest frame. So this is exactly this definition. Take the spatial components of this Pauli-Lubánski vector in the rest frame. This defines this notion of intrinsic spin, which takes this form here. And this object, you can see that it's super-translation invariant, satisfies an SO3 algebra, transforms covariantly under rotations, although it's not preserved by boost. Moreover, you can also verify that this intrinsic spin corresponds to the rotation vector if you go to the rest frame. So it's really the angular momentum vector in the rest frame. So in this sense, this intrinsic spin implements this action of this isotropy subalgebra SO3, and the relation, in fact, is this famous relation between the square of the spatial components and the square of the Pauli-Lubánski with the mass square that appears in between the two of them. Now, there is a third object that you could introduce, which is this intrinsic angular momentum. And this is defined as an object. Basically, what you do is you take the full Lorentz generators and you subtract the orbital part of the angular momentum. So this object basically requires an introduction of coordinates, as also Massimo was mentioned yesterday. And it is translation invariant by construction. But the price to pay, in a sense, is that you need to introduce this translation Goldstone mold, which are conjugate to the p mu. So these are objects that a priori lives outside of the Poincaré algebra, and you need to extend. So somehow you need to extend your algebra introducing these Goldstone modes, and then you can define an object that is translation invariant. And this is what Massimo was doing yesterday. What I want to stress is that fixing the origin is different from defining the spin through this intrinsic definition above. Yeah. Mm-hmm. Yeah. That's what I'm saying. It's two different things. In this case, to define this intrinsic momentum, you need to do it, but for the Pauli-Lubánski vector, this is not necessary. It's something that it's insensitive to the introduction of the coordinates. And so that's why I want to say these are very two different things, even though they both give you an object which is invariant under translations. Okay. So now let's introduce the GBMS algebra. So the reason why we want to talk about GBMS is because it has the feature that in this case, when we enlarge the group, there is an isotropy algebra, which is not trivial, like in the case of BMS. And in fact, there is an infinite set of Casimirs associated to the isotropy algebra of GBMS. So the way we're going to show this is to, this group, it's an infinite dimensional group for each point of scry. So the representation theory of this group is brutal. But what you can do is to do a semi-classical analysis starting from the coadjoint orbits, study the coadjoint orbits, which is in a sense a classical analog of the representation theory analysis. And then if you assume that there is a phase space where there is an Hamiltonian action of a GBMS, you can define a moment map as a map from this phase space to the dual of this algebra GBMS. That, allow you to pull back quantities from the dual algebra to the phase space, so that then you can translate every statement that you make at the algebraic level into the gravitational phase space level. So you can define the map, pull back the Casimirs of this isotropy algebra to the gravitational phase space. So this is the strategy, and for 90% of my talk, so I'm going to work at the level of the coadjoint orbits. I'm not going to talk about the gravitational phase space at this point, okay? Yeah. Which notion spins? It depends on the choice of these coordinates. You could find some coordinates such that this object eventually match this thing here, but it's a very specific case. In general, there are two different things. Yeah, they generate this. The full Lorentz. This guy. You need to restrict the smearing fields if you want to recover just the angular momentum, the SO3. Okay, so let's introduce this GBMS algebra. In GBMS, the important thing to realize is that all you need to do is to introduce a notion of a reference area form on scry, which I indicate here with this epsilon. So this is the area form that you need to fix. And then GBMS preserves this area form. In particular, you can introduce a two-sphere metric, gamma, AB, and which is compatible with this area form in the sense that the square root of the determinant of this metric match the area density that you've chosen as your reference metric area form. And then these are preserved by GBMS transformations. So, but this gamma a priori could be a generic gamma, doesn't need to be a round sphere gamma, okay? And then you can label the vector fields that generates this algebra by function on the sphere, this T sigma, these are the super translation generators, and the vector field Y on the sphere that enters in this component here, and also here with this Y factor, which is given by the divergence of this Y. This curly D is the connection compatible with this metric gamma. You can then compute the Lie bracket of these vector fields, and this is what gives the GBMS algebra. So the Lie bracket gives these vector fields with these functions y12 and t12, which takes this form here. So this is the Lie bracket on the sphere, and this is the expression for the t12. And from this, you can recognize that the form of the algebra takes this semi-direct sum, where you have the diffeomorphism on the sphere, and then you have this function on the sphere that labels the super translations. So as I was saying, this -1 here corresponds to the conformal weight, namely these are the space of functions on the celestial sphere, which transforms with the conformal weight delta. What I mean is that I can take a space of spin S tensor fields of a given weight delta, namely these are symmetric and traceless tensors, control tensors. So all these indices are symmetrized, and I take the trace-free part of this. And then I look at how this object transforms under super rotation. And the coefficient in front of the conformal factor, this Wy, is given by the difference between the spin S and this conformal weight. So this delta that enters here is this number here. Okay, so for instance, for T, it is a spin 0 object, and it transforms with a conformal weight 1, and the Y as a spin -1 and conformal weight -1. So this will be useful because it will allow us to compare in a second object in GBMS with other algebras, the same algebra of systems which have these different conformal weights. Okay. So now let's introduce the dual of this algebra. The dual of this algebra is labeled by a mass aspect M, which is dual to the super translation, and there is an angular momentum aspect J, which is dual to these vector fields Y. And then we can, since this is a local group on the sphere, we can integrate this mass aspect and the angular momentum aspect on the sphere with this dual object, and this defines the charges. So this is the momentum charge, the supermomentum charge, and this is the super angular momentum charge. And the sum of the two define the pairing between the algebra and the dual algebra. So this pairing is defined by the sum of these two charges. And we can use this pairing then to extract what is the coadjoint action of elements of GBMS on the dual algebra GBMS star. Namely, we define the coadjoint action through this pairing using the GBMS algebra in this way. So from this definition, since we know what is the GBMS algebra, we know what these functions are, you can do integration by parts on the sphere, basically, and then read off the coadjoint action on the mass and angular momentum aspect, and this is the expressions that you get. So in particular, you see that M lives in as conformal weight 3, spin 0, while the angular momentum has conformal weight 3 and spin 1. That's how you get this 2 here. It's 3 minus 1 is 2, 3 minus 0 is 3. Okay? And the sum of the two lives in the conformal weight 0, 2, and spin 0. So this object, when you integrate on the sphere, becomes diffeomorphism invariant. It's a conformal weight 2 is an object that you can integrate on the sphere, and it is diffeomorphism. Okay, now we want to study the Casimirs of this associated with this coadjoint action. And here, that's why these conformal weights are useful, because this algebra, the GBMS algebra, is very similar to an algebra that people have studied back in the days when they looked at baryotropic fluids. This algebra defines the systems also as this structure. There is a semi-direct sum of a diff S times this function on this field, where now the conformal weight is 0, is no longer minus 1. So the variables that parameterize the dual of this algebra are the density of the fluid, which has conformal weight 2, and then there is a momentum of the fluid, which has conformal weight 1. And the Casimirs of this algebra was constructed by Laurent and friends in this paper, and through the notion of entrophies. So the entrophies are basically the moments of the vorticity, which is defined in this way. So you take the zero derivative of the momentum, and the moments of this object defines all the Casimirs of this algebra here. So we want to do the same thing, but what we need to do now to do the same thing in GBMS, we have to match these conformal weights to what we had for the mass and for the angular momentum. So remember that the mass was conformal weight 3, so we can define the analog of the density of the fluid by taking a power 2/3 of the mass. So we go from conformal weight 3 to conformal weight 2 in this case. And for the momentum, for the angular momentum, what we need to do is to multiply the angular momentum aspect by this rho minus 1 that take us from 3 to 1. So with these scale quantities now behave exactly as those for the baryotropic fluids. This also resembles a lot this picture of null infinity as a Carrollian fluid. And we can look at the transformation properties of these new quantities, this density and this momentum. So immediately you can see that, okay, the rho is super translation invariant because it's just the power of the mass, and it transforms as a density under super rotations, and P has these transformation properties under super translation, super rotations. So we can construct now the analog of the vorticity for the fluid, which is defined by this quantity here, where this epsilon B is just this tensor that enters the definition of the area form. And you can check, you use these properties here, transformation here, so you can verify that it is invariant to super translations and transforms again as a density under super rotations. In this way, yeah. There is no ambiguity in the sense that you mean this power or? Well, we want to use elements that labels the dual GBMS algebra. We don't want to introduce extra fields. So, yeah. The questions? So now you see that if you integrate this object on the sphere, you can take n powers of this object and multiply with rho, and this quantity here are all the Casimirs. So this would be the analog of these moments of these entrophies for the fluid in the case of GBMS. You have an infinite tower of Casimirs labeled by this integer n and defined by this vorticity W and this object rho. You can immediately verify that if you, or in fact, these objects are both super translation and super rotation invariants using these transformations here for ρ and for W. Yeah. Yeah. Right. So I'm doing the analog of the positive mass representation theory and of Poincaré.
Do you have an analog?
We haven't looked at the case where the massless case. It would be probably more complicated, but a priori, I guess it can be. Yeah. I'm assuming I can invert this this object. Yes. Thank you for. Okay, so we constructed the Casimirs. Now we want to extrapolate what is the analog of the spin generator for this algebra, and in order to do that, we need to first define the isotropy subalgebra of GBMS, and then introduce the generators of the isotropy subalgebra. So we do the same thing that we would do for Poincaré. We fix an element in the dual ideal. So we choose a given mass aspect, and we look for the GBMS transformation that preserves this mass aspect. So we can write the transformation of the mass aspect. And if you recognize that you can repackage this transformation in this way, namely, you can rewrite it as the divergence that of y, where, with a measure now, which is a rescaled measure, is no longer the origin of 1 epsilon, but you have to rescale it by this ρ, and define the divergence with respect to this new measure. Then you see that immediately that the transformation that preserve this mass aspect are the area preserved in diffeomorphism with respect to this new measure ρ. So in this sense, you can define the isotropy subalgebra as exactly this, area preserved diffeomorphism with respect to this new measure, and of course the supertranslations because they don't act on M, so they trivially preserve M. The generators of this isotropy algebra are the vector fields which you can parameterize in terms of a function on the sphere, chi, with this rescale object ρ minus 1 in front. And look, if you just look at the Lie bracket of these vector fields, you reproduce this algebra where now this bracket between the fields is defined this way. So you have to rescale the Poisson bracket on the sphere by, again, this ρ minus 1. So these are the vector fields that basically generates this isotropy algebra here. So from this, you can construct the generators that represent this algebra, and the generators again are constructed using the vorticity W. There is this ρ, and then you take a generic function on the sphere to smear this object. You integrate over the sphere, and this quantity here has two properties. It is again supertranslation invariant. It transforms covariantly under super rotations and reproduce exactly this algebra of the isotropy subalgebra of GBMS. You can verify from these transformations and the one for ρ that this algebra is reproduced at the level of the charges. So this would be this object satisfies the true property that would define this the spin generator, namely it is invariant as supertranslation and generates the isotropy algebra of GBMS. So that's what we will call the spin generator. In exact the same. No, just in analogy with what one would do in Poincaré. These are the two defining aspects of the spin generator. And notice that this object is completely cut independent. I haven't introduced any notion of cut so far. So it makes the supertranslation, the center of mass ambiguity, semi-irrelevant in all this discussion. I didn't have to choose any cut or fix any frame so far to define this object. So chi is just, if you, next slide, right? Yeah, so this is just a function that labels vector fields that produce this algebra. This algebra here, the area preserved diffeomorphism with this measure is defined by basically this bracket here. So these are the vector fields that, you can show that this object have this property here. If you define y in this way, you take the divergence with respect to this measure of this object, this gives you 0. So these are the generator of this algebra, and the bracket that they satisfy, the Lie bracket, is this quantity here. So you want to find generators that reproduce this bracket. That's the goal. magnetic interpretation for this. Yeah, I mean, it's just rescale. Yeah, if you ignore this rescaling, this would be the boost. Yeah, it's this rescaling that it's crucial to have this property here. Okay, so I could stop here and tell you, okay, this is the object that you need to introduce to talk about spin and GR. Yeah. To reproduce this algebra, no, you need to. The Casimir, yes, you can, but if you want to reproduce the algebra of the isotropy algebra, you need to, it's important to have. Well, I mean, you can relate the first Casimir to the square of this spin vector, but then you have all the higher Casimirs in addition to that. Yeah, Casimir. But of course, this object commutes with itself, right? So if I want to talk about the Pauli Lubánski vector, I need to define an object which has a non-trivial algebra. And that's why I talk about the Pauli Lubánski vector. Okay, so as I was saying, I could stop here and this paper would be out 2 years ago. Now, the rest of the talk is about basically relating all this analysis to what people have done previously in the context of BMS and Poincaré, and understand how you can embed these subalgebras inside GBMS and relate this spin generator to cases that people have considered before in the literature. So what took us so long was to actually do this connection. And in particular, so the first thing to understand is how to embed a Poincaré subalgebra inside GBMS. And the idea here is that this embedding can be understood as a symmetry breaking pattern. So given, if you are given a round sphere metric QAB, then, and if you give me an angular momentum aspect, there is a way to, you can uniquely define a BMS subalgebra inside GBMS. And similarly, if in addition to that, you also specify a mass aspect, you can uniquely define the Poincaré subalgebra inside BMS and inside GBMS. Now, there is an equivalence relation between the mass aspects and the angular momentum aspects. Namely, there exist condensate modes that I call C0, which is the super translation condensate, and C1AB, the super Lorentz one, that defines an equivalence class in the sense that two mass aspects that differ by this quantity here, where this CAB 0 is, again, it's just two derivatives of the super translation condensate, and two angular momentum aspects that differ by this object here, which relates to the super Lorentz condensate. They belong to the same equivalence class in the sense that the Poincaré subalgebra associated to these two different aspects are the same. So there is this equivalence class, and in this sense, we can see these condensates as dual to the Goldstone modes, in the sense that they represent the geometry of the quotient space between BMS and Poincaré, in this C0, and GBMS and BMS for the super Lorentz condensate C1. So what they're doing, these two set of condensates, is to label all the possible Poincaré vacua that you have inside GBMS. And as I was saying, these are dual to the Goldstone modes that people have introduced for super translation and super rotations in a very precise sense. It's called condensate because it's conjugate to a Goldstone, basically, like borrowing terminology from condensed matter literature. Now, if we want to be a bit more specific about this embedding, what we can do is to, so we can start with a given general non-round sphere metric gamma, and then we know that we want to find, okay, what is the corresponding Poincaré subalgebra associated to a generic gamma, and what one can show is that this is exactly the same Poincaré algebra that you would have for a round sphere metric Q, which you can define in this way. So given any gamma, you can always find the QAB such that you can rewrite gamma as a conformal factor here, and this round sphere metric QAB, and the conformal factor is fixed once you tell me what is Q, such that R of Q is true. So in this sense, this is a round sphere metric, satisfy the property that the curvature is constant. And then the Poincaré subalgebra associated with this general metric gamma is defined by basically in this way. So you need to introduce first a given stress tensor associated to the metric gamma, which is defined as the unique symmetric traceless tensor satisfies this property here. And then the set of Poincaré transformations that satisfy these properties are the ones that define the Poincaré subalgebra inside GBMS associated to a given metric gamma. This is just the conformal equation basically for the vector fields, and these are the definition of the parameters of the supertranslations. There is a 4-parameter space of solution to this equation that are given by this labeled by these 4 constant x mu here. These are null vectors and ring, which these are the null vectors of the round sphere. So this object satisfies this equation. This label the supertranslation. From them you can construct these y's and define the embedding of Poincaré algebra inside the GBMS, and there is this relation. They are the same up to rescaling of the supertranslation parameter t. So the same Poincaré that you have for Q and for gamma up to this rescaling. Okay, so you can do this even more pragmatically. I'm not going to go through these details because it's not really necessary, but maybe people are more familiar with maybe people have seen in the before this kind of relations here where you introduce this, you embed basically the true sphere in a Minkowski space by introducing these null vectors and using the properties of the spatial components of these null vectors, which are these very useful relations. You can define the boost generators and the angular momentum and the rotation generators, and define the generators of the Lorentz group and the for momentum using these null vectors. But it's exactly the same construction. So I can come back to this if you have questions, but I would skip this since getting closer. Now, as I mentioned at the beginning, there is an important role played by the notion of rest frame in Poincaré, and the question is there such a notion in GBMS? Because so far, in the literature, in the BMS literature, people have concentrated a lot on the notion of a center of mass frame, but not as much on the notion of rest frame. And in fact, if you start with GBMS, there are two different notional frames, two particular notional frames that one can introduce. So what you do is, okay, let's start with a given diffeomorphism on the sphere that maps certain coordinates on the sphere to other set of coordinates that I denote with f of a here. Then you can construct a density such that the area density that the area form that you introduce at the beginning satisfies this property here. So it transforms under this diffeomorphism in this way, where this rho f is a conformal factor. It takes this expression here. And from this conformal factor, then you can read off the transformation property of the mass, the scalar curvature, and the angular momentum aspect under a generic diffeomorphism on the sphere. So these are the transformation property for a general diffeomorphism on the sphere of these quantities. And through this transformation, you can define two notional frames. The usual Bondi frame, which is the case where the curvature is constant, but you can see that in that case, in general, the mass is no longer constant. Or you can choose what we call the rest frame, where the mass is constant, but now the curvature is no longer constant. So you see that in general, in BMS, you cannot be in both frames at the same time, only in the very restrictive case in which you are in a stationary space-time. If you are in a stationary space-time, then it is possible to actually be in the rest frame and the Bondi frame at the same time. In particular, you can see that if you impose this condition of stationarity on these aspects and on the shear, you can go to go to a frame where the mass is constant, and you can also go to a frame where the angular momentum is also, so this quantity here is constant. These are the unit vectors that I was talking about earlier. And you need also, so in general, there would be also magnetic, electric components to this angular momentum aspect. But if you go to, you do a super translation, you go to a center of mass frame, you can kill them. So you only end up with magnetic components of L equal 1 harmonics of the angular momentum. So you can restrict to these two specific forms of mass aspect, which is constant, and angular momentum aspect, which only has L equal 1 magnetic components. And then you can ask, okay, if I now do a boost, how this quantity transform? So what you need to do is to use the general transformation property and find the conformal factor associated to a boost. You can define it by looking at how this Ni transforms under a boost. So you go from like a rest frame vectors and you want to map it into a uninormal vector of this form. And you find that the conformal factor takes this expression here in terms, again, of the velocity that defines the hyperboloid where you map to. And this Net is just this vector which contains only the spatial components of these Ni's. And if you plug in this expression, the previous transformation law, you find that the mass aspect transforms in this way, and the angular momentum aspect transforms in this way. So these are the expressions for the bonding mass and angular momentum if you are in a general boosted frame. Now, okay, now that we have this quantity at hand, we can ask the question, is there, so since we know that in the case of a constant mass, there is an isotropy subalgebra of BMS that reproduce the isomorphic to SU2. Is there a way that you can use the spin generator I introduced before to define this Pauli-Lubánski generator? And you can actually do that. So what first you need to do is to smear the spin generator with this function here. So this rho, again, is mass to the 2/3. These are these null vectors nu. And this quantity here now satisfies the property again. It's, of course, it's super translation invariant and transforms covariantly under the Lorentz generators. However, since I haven't imposed any condition on the mass aspect, you can see that the algebra they satisfy, it doesn't close. This doesn't close as an algebra in general. But if imposed that the mass aspect now is the one of the boosted, is the boosted mass that I introduced before. So recall this rho is m to the 2/3. So from the general expression of this mass aspect in the boosted frame, I can write down what is the boosted rho. And if I introduce this boosted rho inside this quantity here, you can actually show that if you rescale this SI with this power of m, you define exactly the spatial components of the angular moment of the Pauli-Lubánski vectors that I was mentioning before, Poincaré, Carrollian Y introduced a bit earlier. And also you can verify that this object satisfies the Pauli-Lubánski, the analog of the Pauli-Lubánski pseudo-vector algebra. So you can recover this the Poincaré definition by restricting to these boosted mass aspects. Another thing you can do then is to decompose these mass aspects, and you can define, so if you start with the global momentum, defined this way, then you can read off the L0 and L1 components of this angular momentum, and then understand these condensates as the components of the mass aspect for L bigger than 1. So you can rewrite the mass aspect in terms of this L01, and these condensates now tell you which are the components inside the mass aspect that corresponds to the higher harmonics. You can show this by taking the boosted mass aspect and re-expressing it in this form, and you find that the condensate gives you this quantity here. So this condensate that takes this form, it might be familiar to someone that have seen soft theorems before, because this is exactly, I mean, if you take the difference of this object at u plus infinity, u minus infinity, you recover exactly the soft vector in the leading soft graviton theorem. So the punchline here is that this condensate that describe this symmetry breaking pattern from BMS to from GBMS to Poincaré are basically encode this, the information about the soft theorems. So there is this nice interplay between the soft theorems and the symmetry breaking pattern that appears using this the notion of this condensate. Why am I doing this? Because now, as I anticipated earlier, you can look, okay, what happens if I have more than one particle? So in the case of, for instance, two particles, the mass aspect takes this form, is the sum of the two boosted masses. But if I want to check if this belongs to the orbit of the constant mass aspect, namely if I take the boosted mass for a single object which has the total momentum P1 plus P2, I want to compare this mass aspect with this one and check if they're the same. And you can see that for L01, in fact, they are the same, but as soon as you go to the higher harmonics, the condensates of this configuration and the condensate of this configuration are different from each other. What does it mean? It means that if you have more than one particle, you cannot be in the constant mass coadjoint orbit. So you cannot use this notion of Pauli-Lubánski generator that reproduces the SU2 Lie algebra. You need necessary to be in a bigger group, which is the GBMS group, if you want to describe symmetries for a scattering process that involves more than one particle. And finally, you can do the same job for the angular momentum aspect. You can rewrite the angular momentum aspect as a L1 component plus something that depends on this condensate. And after pretty painful calculation, using the expression of the angular momentum aspect in the boosted frame, you can see that, okay, you recover for L1 harmonic the constant piece that it's here, the L equal 1, and this condensate takes this form here, which again, if you take the difference between u plus and minus infinity, gives you back the subleading subvector. So this interplay between condensate, symmetry breaking, and soft theorems seems to be quite robust, at least at the subleading order. I didn't dare to do the calculation for the spin-to charge, but yeah. Sorry? Multiprobe? I mean, at this point, I haven't done any amplitude calculation here. I'm just looking at the mass aspects in the case of multi-particle states. So I'm not talking about, okay, how to do the multiple limits in an amplitude. Mm-hmm. I haven't thought about that. It's a good suggestion actually. Yeah, we're just trying to understand actually how this symmetry pattern really works. And it's the appearance of these soft vectors. It's somehow quite intriguing, but we haven't really explored the implications of this yet. No, you're talking about the soft charge, right? The memory. This is the eigenvalue of the hard charge. This is the operator, the x on the amplitude when you remove the soft graviton. That's what soft vector means. You're talking about the memory. Yeah. The software tells you how to relate this to the memory, basically. Yeah. Yeah. Okay, so last part, I'll be very brief. The moment map, okay, again, here, that's where the peeling enters. So if I assume the standard fall-off for the biscalars and introduce this data as the leading terms in these biscalars, then I have this notion of complex dual mass, covariant momentum, spin-to charge that we saw. These are the radiative data, psi4, psi3. And you can define a non-radiative phase space by setting these quantities to 0. So this is the radiative data, and on top of that, you also kill the dual mass, so the magnetic part of the mass. And this provides the phase space on which there is an Hamiltonian action of this GBMS. In fact, you can, from the equation of motion for the mass and the angular momentum, you can define, you can check that these quantities charged here are constant, conserved in time. So they parameterize the non-radiative phase space. There is by now quite strong consensus on the form of these charges. And by looking at the transformation properties of these charges under GBMS, you recognize immediately this is exactly the same transformation, the coadjoint action that I showed you before. So the moment map becomes like an identity map between this phase space and GBMS star, where the mass is just this covariant mass and the angular momentum aspect is this object here, so that you can immediately translate all these algebraic quantities into phase space quantities. This also is compatible with results that has been obtained before by Glenn Roman, and there's been also interesting work on the coadjoint orbit in the case of the corner symmetry group at finite distance. And yes, I think I stop here. This is the basic summary of the, so I was saying, we try to reproduce all the steps that we usually you would do in Poincaré, in GBMS, and introducing this notion of isotropy algebra in the massive case that has this form here. This is spin generator. This is an infinite set of Casimirs, and you can connect with in specific cases you can connect with quantities that people have derived before in the case of Poincaré. So I stop here. Thanks.